All right, we're going to go ahead and get started. Thank you all for coming. Very excited to welcome you to CFAIL 2023. I'm Allison Bishop, the General Chair. This is the 5th edition of CFAIL. Our original intent was to be a one-time conference, so we failed at that already off the bat, but we're very excited now to be doing this as a yearly event. A big thank you to all the people who've made this possible by submitting their papers, by serving on the program committee. As a reward for those people, we have some special t-shirt swag up here. So if you're on the program committee or if you submitted a paper, you can come and pick one up. Our theme this year is It's My Paper, and I'll fail if I want to. So our t-shirts do have that theme. If you like the t-shirts and you would like a chance to win one, please come back to our open problem session that we're doing new this year from about 4 to 5, where we will be discussing open problems in groups, and then there'll be a chance for people to come up and present some, and the most interesting open problems will win a CFAIL t-shirt. So that's the plan for later in the day. We have 3 half-hour talks today and 1 hour-long invited talk. And our first talk is going to be given remotely by Samuel Jacques on bogus quantum algorithms. So I'll go ahead and let him get started.
Hello. You can hear me and see everything?
Yes. Yep, looks good.
Great. Thanks for the introduction. I wanted to talk about bogus quantum algorithms, which begs an immediate question of what is a bogus algorithm? And to me, it's an algorithm that you come up with and it looks really good. It looks like it does some incredible thing. But then you look at it more closely and you discover that there's some tiny critical flaw that makes the whole thing fail. And classically, if you come up with this, you just come up with normal computer code, you can run it and test it and discover, oh, on line 55, something is missing. But with a quantum computer, it's a little more difficult because you can't run the thing. So you need to debug on pen and paper, and that is more difficult, more prone to error, and also, I think, a bit more instructive. So what I want to present are some algorithms that I've come up with and sort of had this rush of, oh, wow, this is something incredible, before I looked a little more closely and discovered that, in fact, it was not. And the thing is, the errors that I made, I think, are actually fairly common, and I kind of see similar things pop up every now and then. So I think it's instructive to look at these and look at these errors. Now, unfortunately, this is going to be kind of a little bit deep into the technical details of these quantum algorithms. So if you're not used to quantum algorithms, this might not be very informative. If you are used to quantum algorithms, I strongly encourage you to pay very close attention and see if you can spot the problem before I reveal what the problem was. So I'll get right into it. And basically what we're going to do first is solve generic search problems in linear time. And a generic search is you're given some function, and you want to find a unique input that produces a particular output. So think about a pre-image attack or just a known plaintext ciphertext attack. And the quantum algorithm that works for this is Grover, and it has this square root speedup. It takes the square root of 2 to the n. And the thing about it is that if your function actually has some secret, then after 2 to the n calls, it gives you exactly that secret as the unique output state. But if there was no solution, then actually it gives you a uniform superposition of all the inputs. And this distinction is what I'm going to use here. And the idea is that we will partially guess this function. So we'll split up the input into blocks of size k. So rather than having x have n bits, we have m blocks. And what we're going to do is pick some value for the first, all but the last block, and then partially evaluate the function. So that means that every tuple that we picked for the first n m-1 blocks will define a different partially evaluated function only on the last block. So you give it input x, it inputs your guess for the first m-1 and then evaluates on x. And then we can run a Grover search just on this function. So the search space has decreased. So we're just searching over a smaller space, but of course there's really high odds that we guessed incorrectly. And if we did guess correctly, then the outcome that this produces is just the secret block. So it tells us what the last block is for our secret state S. But if we guessed wrongly, then the outcome is the uniform superposition over all these k-bit strings. And to make this into a quantum algorithm, rather than having this guess, we'll actually make a superposition. So we'll have a superposition over all of the guesses we could have made for the first m-1 blocks, and use those as inputs into F and run a Grover search over the final bits. And because quantum operations are linear, this means that basically it's like we're doing all these Grover searches simultaneously on the last block. So for each possible function we could come up with by partially evaluating, we're doing a Grover search on it and kind of getting the result all in superposition. And looking at each state and seeing what happens, if we guessed wrong, then we take these m-1 blocks, we do the Grover search, and we come up with this uniform superposition. If we guessed right, we do the Grover search and we get this thing. And the interesting thing here is this normalizing factor. So we have 1 over root 2 to the k here, and nothing here, so basically a 1. So we've made the state with the secret a factor of square root 2 to the k larger. So that's pretty good. So summarizing the algorithm, we make this uniform superposition on each block, use the first m-1 to define a function on the last block, and do the Grover search. And all our wrong guesses don't really change because we started with a uniform superposition and we just stayed there. Grover didn't really do anything, but the right guess got this much larger. So naturally, we'll move on to the next block. So we can basically just define another function. We partially evaluate on all but the second last block, and we start this search from the outcome of the last search. And it basically has the same property. If our guess was correct for all but the second last block, or if it was incorrect, we get a uniform superposition. And if it was the correct block, we get exactly the secret. And so now, just like before, this has bumped up the amplitude of the secret state by a square root of 2 to the k. And so every block that we do, we increase the amplitude by this factor of root 2 to the k. And we said that n is m times k. So once we do this over m blocks, we get 2 to the k to the power of m. So this will be square root 2 to the n. And that was the amplitude of the secret state that we started with. So the amplitude of the secret state is now 1. It's the only state left. We measure it with certainty. We get the secret state. So we solved our search problem. And we can look at the complexity. Each k-bit input Grover search has complexity square root 2 to the k. And we do n over k searches. So the total cost is this. But if we take k to be a constant, then this is O of n. So we've solved generic search, linear in n. This shouldn't happen. So something has gone wrong here. I've lied to you somewhere. This algorithm doesn't work. And the problem that, again, comes up in a few places is Grover's algorithm must start from the 0 state. And what do I mean by that? Well, let's get into what Grover's algorithm actually is. It's an iteration of 2 quantum operations. One of them is the oracle. So it looks at the state and checks the function, whether it's the secret state, and adds a phase. And this is the thing that seems to get a lot of the attention. You design nice circuits to do this. But equally important is this diffusion operator, which adds a phase to the superposition you started with. And it seems a little odd to kind of detect a superposition and add a phase to it. Like, what does that even really mean? But really, you can think about, take that and do sort of a basis change. How do you detect this? What you do is you make an operator that maps the 0 state, which is a nice, easy one. You can initialize qubits in 0. You can detect the 0 with a bunch of AND gates. I guess OR gates would be what you'd use to detect 0 instead of 1. It's the same idea. And what you do is you have this operator that maps your 0 to your superposition that you started with. And quantum operators are easy to invert. So you just apply the inverse, and then you add a phase to this state, the 0 state, which is easy. Then you map it back to your superposition again. So it's sort of like you do a basis change to a basis where it's very easy to detect this superposition. But that means that you need this operator that I called U sub d. If you don't have that operator, you just can't do a Grover search because you can't detect the superposition that you need for this diffusion operator. And this is getting a little bit abstract, so let's look at why this makes this block-wise Grover fail, where it adds the bogosity to this algorithm. So the first search, what I said is everything was correct. But when we start the next search on the second last block, we don't have a uniform superposition anymore. We have something that looks like this. So we've got our secret state being kind of larger. And more or less, it means it's entangled with the other registers because we get more amplitude on this depending on what the other values are. And if we want to map the second last block to the 0 state, we need to kind of uncompute and get rid of that entanglement to sort of refresh things. And the only way to do this really is to undo the first Grover search. So we do the Grover search to get to the state, but then to start the one in the next block, we have to undo it to detect the uniform superposition again. So every iteration in the next search must redo the entire search on the last block. So every iteration has to cost O of root 2 to the k. And we're doing another root 2 to the k, so now we lost our square root, we're already at 2 to the k, and this is just going to keep getting worse the more blocks we do. So the Grover search on each block must repeat the searches on all of the previous blocks as part of its own diffusion operator. So the cost doesn't grow linearly with the block size, it grows, or with the number of blocks, it grows exponentially. And so the final cost is root 2 to the k to the m, which, as you would expect, is root 2 to the n. So this kind of technique can be useful. You can sort of hide costs of the function, but ultimately it still has to work. It still has to be an exponential complexity. So my takeaways for quantum algorithm design is to always remember you cannot freely start your Grover search from any superposition. You can start it from things that aren't uniform, but if you do that, you need to have some sort of method to create the superposition, and you need to include the cost to create that in every iteration of your Grover search. And at the end of the day, generic search is still exponentially hard, which, if you're a cryptanalyst or a designer, is a good or bad news. And that was sort of the first bogus algorithm. I'll move on to another one that is a bit more subtle because the conclusion is less striking. And what we're going to do is look at the group action problem. And in this case, you're given a group, and let's say it's an abelian group, and it acts on a set X. You denote this by G star X. And you're given 2 elements in this set, and you want to find a secret element of the group such that when it acts on X, it gives you Y. This sort of looks like discrete log, and it basically is the group action version of discrete log. It's what makes CSIDE, the isogeny protocol, hard. And as far as we know, it's sub-exponentially hard for quantum computers, and there's an algorithm that does this. But what we'll do now is do it in polynomial time, as long as the order of the group is smooth. And to do this, we start with a superposition of 0 and 1. This is easy to do, and we use this to control the group acting on X or Y. So what I mean here is we have some classical circuit that computes the group action, and it's well known that you can take any classical circuit and build a quantum circuit to do the same thing in superposition. So we make a superposition of all G's. We apply this circuit based on whether to act on X and Y, which we kind of know classically, those are inputs to our problem. And we use the first qubit to control which one happens. So we have something over X and something over Y. And I'm going to make this simpler and assume that G is cyclic so that we can actually take some generator and just think about G to the I for a bunch of I. So I'll switch the sums to have just G to the I. It's the same thing, but it makes it kind of easier to analyze. But because I said that this group is smooth order, we can take this subgroup of just the n over p order subgroup and make a superposition just over that. So we're doing kind of treating G to the p as a generator of some subgroup and only going up to n over p minus 1. And now remember that Y is going to be some secret acting on X. And I'll say that this is G to the S times X. So I'll kind of abuse notation and use S for the exponent. And so I can write this as the kind of the part within this subgroup, and then the coset that it belongs to. So sort of just dividing by P. And then I'll kind of rewrite the state above down here by just substituting things. So first I say that Y is G to the S acting on X. And then break open S into these 2 parts. Combine these together into the exponent, because that's what a group action does. And then combine the parts that are multiplied by P. And then the thing to note is that this is kind of just a sum over all of this subgroup. And so I could just re-index the sum, and it would look exactly the same as it did up here. So I could just replace the index by I. So this other part of the secret that is in this subgroup gets absorbed into the sum because we have this superposition over all the elements. It's sort of invariant under kind of acting by anything from the subgroup. And this is really nice because now we can take this state and we pick some random t between 0 and p minus 1, and we use the first qubit to control acting on it by g to the t. So we use 0 to control acting on g to the t, so it changes the state to this. And I'll rewrite this a little bit so that it looks like this state. Kind of now we have superpositions over two different cosets of this subgroup. And well, it might not even be two different cosets if we guess t correctly. So rewriting the state like this, we've got the a and the b. If we guessed correctly, then a is equal to b. So we have exactly the same state entangled with 0 as entangled with 1. But if we guessed incorrectly, then these are orthogonal. And they're not just different, they're actually orthogonal because we have two different cosets, and so they have no elements in common, so they're completely orthogonal. We'd really like to be able to distinguish these two cases because then we could test if our guess for t is correct. And this is actually very easy for a quantum computer to do. So all we have to do is apply a Hadamard gate to the first qubit. This is called a Hadamard test. It's kind of a standard technique. Really being fast and loose with notation here, but we end up with something where 0 is entangled with a plus b and 1 is entangled with a minus b. So you can see that if a equals b, this term cancels out and we only have 0 left. So if a equals b, we always measure 0 in this first qubit. And if they're orthogonal, you measure 0 and 1 with equal probability. So you would repeat this test and measure this first qubit, and if you ever measure 1, then you know that they were orthogonal and your guess for t was wrong, so you move on to another t. And if you do, say, 100 of them and it's always 0, fairly good evidence that they were, that you guessed correctly. So this gives kind of the whole algorithm. So we iterate through each prime factor, we iterate through all integers up to that prime factor, and make this kind of n over p torsion Kuperberg state. And then we apply g to the t to the 0 half, and then do this Hadamard test. And we do this enough times to convince ourselves whether we guessed correctly or not. Well, what's the complexity of this? It's polynomial time to make this Kuperberg state. All we have to do is take a classical group action. It's polynomial time, so we just adapt it to this setting. Same with applying g to the t. The Hadamard test is just a Hadamard gate and a measurement. That's a constant number of gates. And solve its polynomial time for each iteration, and so we repeat p times for each factor. So if our group factor is like this, then the cost is kind of the sum of these. So if g is smooth, then the cost is kind of polylogarithmic in the bound of smoothness. And this seems plausible, right? If someone came up with this algorithm and you saw this, I don't think anyone would say, there's no way this could happen, this is a impossible result. But actually, it is also incorrect. It's doing something sneaky that makes the whole thing fail. And the key insight that makes this wrong is to not forget the difference between an in-place operation and out of place. And these concepts don't even really exist in classical computing. But for a quantum computer, they're actually quite different. So when I said that you can make a circuit to have an element G act on a fixed element X, there's two things that I could have meant. The first is that I start with some G, some state G, and I apply the circuit, and it becomes G acting on X. And the original G is sort of gone. And the other version is I have to keep the G around, and I have some kind of hidden 0 states that become G acting on X. The one on the left is much more useful, but actually all of these generic constructions to make quantum circuits out of classical, they always create out-of-place circuits. If you're very lucky, you can sometimes construct an in-place circuit, but it's generally much harder, and sometimes it's impossible. Quantum operations have to be reversible, so if the function you want to compute, like a hash function, is not invertible, you just couldn't create an in-place circuit to do it. And so when I was saying, okay, we can make this circuit because the classical circuit exists, not necessarily true, because it would have to be out of place unless we come up with something better. And this shows where I lied to you. Kuperberg's algorithm does not produce the state on the bottom, which is what I showed you earlier. It produces a state on the top. So you have to keep the index, or sort of the exponent I, that you use to kind of act on x or y here. And the problem with this state is that this absorption that I told you about, where you can re-index the sum, it doesn't really change things. It will change things here, because if I add something to the g, to the exponent of g, and try to change the index, I also have to change the index in this register here, and that's much more noticeable. These two states won't be the same if I do that. So kind of the absorption doesn't happen. If you were able to create this bottom state, everything else I said is completely correct. So is there any way that we could get to this bottom state from the top state and make this attack actually work? Well, can we compute the exponent from this vector? Can we uncompute it? Imagine that we could. We had some circuit U that would do this. Generally speaking, if you have a quantum circuit to do some task, it's very easy to create the inverse circuit, because all of the individual gates are easy to invert. So we could get for the same cost, the inverse of U that would take 0 and this state and produce the exponent in the first register, which is actually a bit problematic, because we could just take our challenge, like the group action challenge that we're trying to find, and apply the same circuit, and it would pop out the secret exponent S. So whoops, we've just solved the group action problem. So the algorithm that I showed you works, but to make it work, you need a circuit. It solves the group action problem, but to make it work, you need a circuit that solves the group action problem as a subroutine. So not super effective. What are the conclusions from this one? The thing that you really need to remember is always assume circuits are out of place until proven otherwise. And this is, again, like, this is a common mistake that happens all the time. I heard recently that Regev actually forgot about this on a draft, not in a devastating way, but the big name, very good at quantum computing, and still kind of forgets about this. The other thing is that don't forget that uncomputing is often very hard. There's a lot of cases where if you can uncompute a certain register, you solve even more impressive problems than this group action. But the other thing is, if you are really into quantum algorithms, I think this kind of superposition state, so the thing that we couldn't create that I said was what Kuperberg's algorithm makes, that would have been really useful if we could have made it. So it's kind of interesting to study creating that superposition as a problem in its own right, and then using that as a resource. So here's another paper that kind of takes a similar, what seems similar to me, about lattice problems. So in the extended abstract, there's actually another bogus algorithm that I didn't have time to talk about that supposedly solves LWE. And my overall lessons, I guess the biggest one that I didn't actually put on the slide is when you see some ePrint that says, here's a quantum algorithm that does some incredible thing, wait a few days, wait for the experts to have a look at it and try to find such mistakes, because often they show up. But if you want to kind of not be you want to be careful with your own results, always make sure you include these costs to make superpositions. Always assume computations are out of place unless you have specifically found a way to do it otherwise. Don't forget the costs of uncomputing states. The thing that I didn't get to talk about was when you're normalizing things. This is often something people do, and they ignore the normalization in quantum algorithms, but it can actually be quite problematic if you forget about it. And the final one is, before you post your breakthrough preprint, maybe run it by a friend. So thank you, and sorry that I failed to be there in person also.
All right, let's thank our speaker. All right, we have some time for questions, so feel free to come up to one of the mics in the room. In the meantime, I have a question. Just put that speaker window in here. Yeah, so I think it's great that you're able to generalize each of these into kind of a principle of a thing that can go wrong in other settings. I wonder if you thought about making this into a sort of bad algorithm generator that could be used for like creating problem sets or examples for people to train those muscles of recognizing these kind of mistakes.
That's an interesting idea, especially because for example, this forgetting about Grover, you've solved an NP complete problem, so really you just kind of chug through the reduction and you could use it anywhere. No, I haven't thought about that, and that might be an interesting kind of bonus resource, is just buckets of these that are the problem is, though, they would be very similar. Kind of once you're looking for these, and if I've told you the algorithm doesn't work, then it's a little easier to spot, oh, here's where you haven't done your Grover iteration properly.
That's just something I encourage people to think about as a way of generating easy CFAIL papers for future years. If you solve that kind of generation problem, you can get free swag for many years to come. So something to think about. Any questions from the audience or from the Zoom audience? All right, let's thank our speaker again, and then we're going to have a coffee break here, and we will come back at 10:45.